Okay, so here we go, topic 2.9. Every operation has exactly one inverse operation. Kids, before you even heard the word inverse or knew anything about inverses, you were using that. Because when you had to solve an equation like x plus 3 equals 7, what did you do? Subtracted 3. So in other words, you used the inverse operation. You undid the addition with a subtraction, and that gave you the answer, right? So how about cubing? How do we undo a cubing? Cube root. Yep, cube root. Every time you solve an equation, you're using these inverses. Now, this is where it gets interesting. What is the inverse of an exponential? How do you undo an exponential? I'll give you a hint. Starts with an L. Logarithms. Logarithms and exponentials are inverses of each other. Okay, so that's it. That's what today we're going to talk about. We're going to talk about this inverse relationship. So, big idea. Just as we can write rational numbers in decimal form and fraction form, we can also write equations in exponential or logarithmic form. So, let's look at example 1. It is absolutely true that 3 squared equals 9. That equation, which is written in exponential form, as an exponent, exponential form, is exactly the same as the log base 3 of 9 equals 2. These two equations mean exactly the same thing. So, example 1a, convert the following from exponential to log form. Right there, that's the log form. Okay, try B, C, and D, and see if you can do that. Same thing. Convert from an exponential into a logarithmic form. Does that look okay to everybody? Now, quite honestly, we don't do that very much. Almost always we're going the other direction, which is what example 2 is about. But it is important that you know these two things are the same. I also want to make a comment about this one. Log base 10 is special. Log base 10 is called common logarithms. These are called common logarithms. Because our number system is base 10, so they're the most commonly used. The symbol is just LOG. So when you press the LOG button on your calculator, there's an implied base 10. Just like when you press this button on the calculator, there's an implied square root with that symbol. Similarly, this guy right here, Euler's constant, E, the letter E, Euler's constant, is extremely valuable and useful. It shows up all over the place. So these logarithms are special. They are called natural logarithms. And you know what their symbol is? ln. Yep, ln. Means log base E. So every time you see an ln, you can leave it ln or you can rewrite it as log base E because that's what it is. Okay. So now it says, do the same thing backwards. So this equation is in logarithmic form, and you're going to rewrite it in exponent form. Okay? Now I I don't know what Mrs. Coors called it last year. We had different teachers call it different things. I call it log rolling. 7 to the second equals X. Some people call it loop-de-loo. I don't know, whatever you want to call it. Somehow you got to translate the logarithmic equation into the exponent form. We do this all the time because now I know what the answer is. Now I know the answer is 49. In a minute we're going to solve some of these. All right, so go ahead and do the other ones. See if you can get the other ones sorted out. You're changing them into their exponent form. Remember, a couple of these didn't have bases, but they actually did. LOG means base 10, so that one is 10 squared equals y. And ln is actually base e, so that's e to the 4th equals c. Everybody okay with that? You've done that before, easy. Okay, example 3. Now we're going to actually evaluate these without a calculator. So you can do this a couple of different ways. But one easy thing to do, I think, is just set an equal to x and then translate it. So this first one, for example, would say 2 to what power is 8? Well, clearly the power is 3. So go ahead and see if you can get all these done. Check your answers with your teammate, and then we'll get our calculators out. But don't use a calculator for these. Ellen, did you get B?
X equals 2.
What does the group think? Good? Perfect. All right, how about C? Joe Funk, what'd you get for C?
5.
Mm-hmm. Yep, don't doubt yourself. 2 to the 5th is 32. That's exactly right. Very good. Now, for D, I went ahead and stuck my 10 in there. So, Jacob Gillard, what'd you get for D? Yeah. Perfect. 10 squared is 100. Yep, perfect. Oh, now we're more interesting here. Anybody get an answer to E? What'd you get?
1/4.
1/4? I think it should be 1/2 because this says 16 to what power is 4? So you might just know that, or you know that 16 is 4 squared. So 4 squared to the x is equal to 4 to the first. So 2x equals 1 and x equals 1/2. If you're not using a calculator, then you're going to have a common base somehow. Okay, you're going to figure that out. All right, how about F, another interesting one. Julia, did you get F? Yeah. 3 to what power is going to give you 1? The only power that can possibly be is 0. And it wouldn't matter. This could be a 4, and it's still 0, right? In fact, your logarithmic curve, you're graphing your logarithmic curve, any base, I'll just say B, base B, any base, is going to go through, unless you have moved it, you know, with a translation or something, it's going to go through the point 1, 0. It has an asymptote at 0 and looks like this. That's what your logarithm function looks like. Always goes through the point 1, 0. Which says, if you plug in 1, you're going to get 0 every time. All right, what about G? What did we get for G? 1. And here's another kind of wacky one. Anybody get an answer to this one? Negative 2, very good. 6 to the negative second, 1 over 6 squared. Very, very good. Okay, now, if we look at the next set of problems, first one is log base 10 of 9. Do you understand why now I need a calculator? There's no way to get a common base with these two numbers. If this had been a 27 or something, I'd be all set. But a 10 and a 9 don't have a common base. So, I'm just going to go straight to my trusty calculator and press log 9. At least 4 places after the decimal, 0.9542. Would you agree with that? Perfect. All right, go ahead and do B. You get 3.7871. No sweat. Now, tell me about problem C. I have a problem. If I am using this on my calculator, these buttons right here, I have a problem because the only 2 logarithm buttons I have are for base 10 and base E, okay? Now, the newer calculators, drat those designers, did build in, you do have a button that will allow you to take whatever base you want. So we're not going there, we're not using that right now. Right now, we're going to do what we would need to do to use a standard calculator, and that is change this to a different base. Either 10 or 8, it doesn't make any difference, but I gotta change it to one that I can type in, okay? So how that's done, it's called the change of base formula, and how it's done is, we go ahead and create or change this into its exponent form. So I change it into my exponent form. Now, we're going to, you can't, 2 to the x equals 10, there's no common base here, so I'm going to take the log of both sides. You can either LOG both sides, or you can LN both sides, whatever you want. I'll LN just for the heck of it, okay? Now, as soon as I do that, this becomes a coefficient, that's one of our properties of logarithms. So x ln 2 equals ln 10. And then I can divide by ln 2 and get the answer to the question. Caution, when you type this in, be sure that you're closing this parentheses before you hit divided by. So ln 10, close parentheses, divided by ln 2. You should have gotten 3.3219. Now, just for fun, what if instead of ln'ing both sides, I would have logged? I'm gonna end up with log 10 over log 2. Would you agree with that? Just type that in, just humor me. Type it in. And it's not gonna matter. So you can ln or log, but those are the two that you wanna use if you're using your standard regular calculator type buttons. Okay? Now, you can certainly, anytime you want, you can go through these steps. They're valid, you can do it. But I want you to notice something. Here was the original problem. And here is what my answer turned out to be. And that will be the case every time. The change of base formula says that this logarithm is all, let me change these numbers. Let's say log A x, let's say that. This is always going to be the log of x divided by the log of A. It's always going to be that. Or ln, you would use ln, same thing. So when I'm teaching like kids that aren't as gifted as you guys, I always say, when I look at this expression, this number is kind of down below, and that goes below in my change of base. So it's always going to be log this over log this. So when I look at letter D, I don't need any fancy buttons on my calculator, although some of you have it. I know that D is going to be log 135 over log 7. About the only way you can mess that up is to forget to close the parentheses, so don't forget that. Did you get 2.5208? Done, every time. So don't worry if you have a base that doesn't work, you can always make it work. Okay? All right, now here is something that you may or may not have ever seen before. It's kind of exciting. When useful purpose for logarithms is when dealing with exponential data. Exponential data can be challenging to display graphically because the values start out really small, but what happens to them pretty quickly? They get very big. So take a look at the graph on the left down there. It shows the population since 1620 of English Americans in the United States. Now, that's a beautiful graph, it's a beautiful exponential, it's doing exactly what we think it should do. But if you had to interpret the data at year 10, 20, 30, 40, 50, 60, you'd have trouble, right? Because it's all smushed down there. And why is it smushed down there? Because you had to have some kind of a scale that went all the way up to 7 million. So an alternative to that would be to use what's called a semi-log plot, where half of it is a logarithmic grid. So look at the graph on the right there. The years at the bottom are exactly the same, but now, what is the scale on your y-axis? It's not a straight, like, numerical scale. It's in powers of 10. So 10, 100, 1,000, and so on. And look what happens to the points when they're plotted with that grid. See how much more understandable it is? Now, what's a downside of the semi-log plot, though? Can you tell me? Would there be anything, any negative to that? Yeah, I mean, it can involve a little more calculating, but what does this show me? What does the actual graph show me, the exponential there? That shows me how fast this thing is growing. Once it gets past the beginning few years, I don't know what's going on down there, it really starts growing. What does this one look more like? It's kind of leveling off almost, still going up, but I don't see that burst that I would see in an exponential. Okay? All right, now you're gonna practice. All right, so let's go to example 5. You need to graph data for your 1820, 1860, and 1880. And remember, these are years after 1620. So after 1620 would be 220. All right, so see if you can plot them. Plot them on this grid, see if you can do it. Were you thinking about changing your raw numbers into scientific notation? So that's how we know they're all between 10 to the 7th and 10 to the 8th? Because aren't all those numbers times 10 to the 7th? And they're just getting a little bit bigger. All right, so let's look at the last problem, example 6. He actually gave you some semi-log plot paper. That's what this is, this grid right here. It's all labeled for you, everything is fine. Now, I want to remind you though, so see how we're going from 1 to 10? Those numbers are counting up by 1. So those vertical line or the horizontal lines. So here's 1, and then here's 10 to the first, or 10. So that first line, that's 2, 3, 4, 5, 6, 7, 8, 9, and then you're at 10. Now we're going from 10 to 100. So what are these? This isn't 11, 12, 13. This is 20, 30, 40, 50, 60, all the way to 100. And then it starts with 200, 300, 400, all the way to 1,000. Okay, go ahead and plot them. Go ahead and plot them. So here's 100. The first line above it is 200, and then the next one's 300. You guys got this figured out? It's brand new. You got it. You're amazingly brilliant people. Okay, 2-9 will be due on Monday. The other day. Oh, yeah. The other day I gave you a 1-page 2-7 to 2-8 review. Did you dig that out? Let's take a look at number 1. This is review. Shouldn't be too hard. All right, so what do we got? F of X. Domain of F. Oh, this is really old. This is old review. This is like algebra 2 review. What's the domain of this guy? -8 on. So the domain would be does that make sense to everybody? What happens if you put -10 in? It's imaginary. Can't have that. So we gotta be bigger than -8. So on our number line, solid. There we go. Okay, that's easy. What about the domain of G? What's the domain of G? Basically everything except 2, right? So in the number line, if we had graph that, it would be open dot at 2 and everything else. Okay. What is the range of F? What is the range of F? So go back to F. Think about Y values. What do you think? Think about if we're going to graph this thing, and we know we're plugging in these numbers. We're plugging in those numbers. Tell me about the outputs. Positive. Aren't they all going to be positive? Starting where? Starting with 1? 0. So your range is 0 to infinity. You guys should probably know what the square root function looks like. If you don't already, you should know what that looks like. That is like half of a sideways parabola. It's the top half of a sideways parabola. So clearly the range of that thing is positive. Adding the 8 just moves it, but it doesn't change the range. Let H be the composition. Some of you were struggling with some of this in the homework. Some of you have turned in that homework, and you're struggling just a little bit with some of this. You need to write the equation of the composition. plug F into G. So that's gonna be G of the square root of x plus 8. So that's gonna be 1 over 3 square roots x plus 8 minus 6. Would you agree with that? So that's my function. What is the domain of H? Any ideas? Drew?
Would be -8 to -4.
Bracket or parentheses?
Bracket.
So -8 to -4?
No. Parentheses are -8.
And did you say -4?
Yeah. And then, negative, or union -4 to infinity.
All right, let's talk about that. Anybody have a different idea? Patrick, what are you thinking about there? I see you looking.
I was just thinking about it, got the -4 now, so. With a few, no worries. Yeah, I got it.
What is Drew thinking about? Where'd that -4 come from?
Can't have a 0 in the bottom.
Can't have a 0 in the denominator. So whatever this is, it cannot be, whatever that all that's in the denominator, it cannot be 0. So I don't know what he did, but you could solve this easily enough. The square root of x plus 8 cannot be 2, which means x plus 8 cannot be 4, which means x cannot be -4. I think that takes care of it. I think that takes care of everything. I don't know that there's anything else we need to worry about. Because this is gonna be fine as long as the denominator's not 0. Okay? Awesome. All right, let's see one more and then I'll stop. Station 2. Number of kids attending camp in UW is given by this. The number of counselors is given by this. What? We've seen this kind of question before. Interpret this. In other words, put into words what that means. What does that mean? Julia,
Well, there are 58 kids, there's 4 camp counselors.
say it again.
And there's 58 kids, there's 4 camp counselors needed.
Okay, so there's one thought. Anybody have a different thought? Josie?
In week 4, there's 58 counselors needed.
So Julia said 58 kids, 4 counselors. And Josie's saying week 4, 58 counselors. Anybody have a different thought? I'm with Josie. This is W right here. What does W stand for? That is the number of weeks, or the week, fourth week of camp. And in the fourth week of camp, this tells me how many kids will be attending. And then C tells me how many counselors I need for that many kids. Neither one of these numbers is kids. That's weeks and that is counselors. What does this mean? I don't know what it equals, but what would it mean? Well, it's the inverse of the K function. So the K function said, at W weeks, we have however many kids. That's what K says. So when I reverse those, what's that 126? That's how many kids there are. So this would tell me what week has 126 kids? Right? And then, which of all these functions would output the number of kids that could be monitored by a given number of camp counselors? So isn't C of K, doesn't that tell you the number of counselors needed for K kids? Isn't that what this is? Okay. Does that help? Which of these functions would output the number of kids that could be monitored by a given number of camp counselors? So this is KC. Give me some kids and I'll tell you how many counselors I need. Aren't they asking for the opposite of that, the reverse of this? So this is this. So what would the inverse of that be? C inverse. Yeah, C inverse. So it's C inverse. All right, well those are some good thought-provoking problems. Hang on to that paper. We'll try to do some more review along the way.